Okay, so let's get started. So let's. So in the last lecture, we were discussing um, how to define new data types, and in particular, we looked at a way of representing binary trees, and we also looked at how binary trees can be used for efficient searching, and we looked at some of the properties of binary trees, balanced binary trees, such as the height being logarithmic in the number of nodes in the tree. So this feature for capturing data structures is quite flexible, and it can be used to represent many other things that we have studied in this course, such as how do you can take a proposition, and we discussed how uh, we discussed propositional formulas and how to evaluate them given some given the values of variable in the propositional formulas, and we could express all of that using a simple program in standard ML. And here is a data type definition which says that a propositional formula is either true or false, or it is a variable, right? Once again, this is just saying var doesn't mean anything. It's just a way for us to represent something that we want to. It's just a string that means to us as it's a variable, but really all that it tells to ML is that there is an index, right? So there's an integer which sort of says what is the number for the variable, right? And then it can be negation of a propositional formula. It can be a conjunction of two propositional formulas, a disjunction of two propositional formulas, uh, you know, or it may be an implication involving two propositional formulas. And then, if you have a formula like this, that's how we normally write it down. We can represent it using this data type in standard ML in this way, right? So we can, if you want to see the structure a little bit more uh, clearly, then we can, what we can do is we can again draw these uh, expressions in a tree form, right? So this is something that we did uh, in the last lecture, where we were talking about how arithmetic expressions and other expressions could be expressed in the form of a tree that captures exactly the nesting of operators. So the same way we could express this uh, expression as a tree. The outermost symbol is an implication, and that has two children. And on the left hand side, there is a conjunction. Then there is x1, x2. On the right hand side, there is a negation, and then, right? So we can express this as a tree. And now it's the same tree that we are representing in ML using this data type, where once again, you can see that uh, I have implication at the outermost level. Then the first child is an and, which has okay. And then the point is that if you have it represented in this form, then you can also start expressing what it means for a propositional formula to be true using another definition like this, which basically says that if you evaluate the formula true, the result is going to be true. If it's false, then the result is going to be false. And then let's take just one example. So if you want to evaluate a conjunction of two formulas, then you first evaluate the first formula F1, and if it is true, and in addition, you evaluate F2, and F2 is also true, then the whole thing is true. So we can express everything that we have studied in ML, and the point is that uh, whatever mathematical definitions we are able to write in class that defines what it means for a formula to be true, the same things can be expressed in a relatively straightforward way in standard ML. So, and the purpose of doing something like this is that if, let's say, you are trying to define the meaning of how do you evaluate the value of a propositional formula, you can either write down uh, in English and informal notation that we have, but then you won't be able to figure out whether it is correct or incorrect. On the other hand, you could write it down in this form, and then you can evaluate your formulas and check that in fact you have correctly expressed the meaning of these formulas, right? So the point is that if you instead of writing it in English and math, if we write it in a programming language like this, which allows you to express mathematical concepts easily, then you have the ability to then evaluate or run your specification, right? So there's a definition of evaluation. You can run this and then see what it produces as the output. So that way you have a way of checking whether your understanding of some concept is correct, right? Uh, so so that sort of goes back to one of the reasons why we insist on being able to uh, clearly and precisely define concepts, because ultimately programming requires you to express your thoughts in a error-free manner, right? So you want to make sure that it's precise, free of ambiguities and errors, and that's when you will have a program that actually does the task that you want to do, right? So writing out things, definitions, and understanding the concepts in this course is basically a way for you to uh, improve the way you think, a way to make sure that you think clearly and you're able to express your thoughts precisely and accurately, and as a result, you are able to get the results of the computation that you want, as opposed to solving a problem different from what you really want to solve. So in the same way, you can also take a predicate formula and once again express it in this using a data type. And you can see that the data type for predicate formula and proposition formula are quite similar, right? So you have the same you know uh, propositional operators like not, and, or, and implication. But of course, you add two more operators. Uh, the quantifiers exist and for all. And then the base case here is a propositional variable. In the case of a predicate formula, the base case is going to be a predicate. So for instance, once again, to give you an example, if you take a predicate formula like this, then that can be expressed in using a data type like this, using an expression like this. And you can, in this case, I already wrote it down in a nested fashion so that you could easily see how things here directly map to the operators here, right? So there's an implication, then P1 of X1 is here, and then there exists is here, the conjunction is here, P1 is the first argument to the conjunction, and P2 The second argument is a conjunction. So you can extend this idea to predicates as well, and try to apply the same idea that if you write down your definition, you can actually evaluate it and check whether your definition is right or wrong, right? The limitation, of course, is that anything that a computer is going to work on is finite, right? So if you want to write something that some property of infinite sets, well, that's not something that you are able to check on a computer, right? At least not directly. So, but otherwise, there are many concepts where the definition itself can be written as a program, and then you can have a way to check your definition. Okay, so that's that's the last bit I wanted to introduce on standard ML. And what we are going to do in the rest of the lecture is to give a quick summary of what we have covered in the course. Before we do that, are there any questions? So we went through a couple of questions in the exam in the last lecture. I am not going to go through the rest unless somebody specifically asks me to do, because the answers to most of the questions are already there. When you look at your your exam, it shows you what the correct solution is, and that's probably tells you how to solve the problem. But if you don't understand, then feel free to ask me a question and we can try to go through that. So everyone is happy to be almost done, right?
I have a question about the finals. Is there going to be any practice tests for the final?
No, I am not planning on giving out any practice tests. But again,
okay,
there are 6 homeworks, right?
Yeah.
So I think that is really your practice.
Okay.
Okay. So what I made, and in addition, you still have the 3 practice midterms that were given out to you, right? The practice midterms. So and between those, I think those should be enough for the point is that I don't want to give you just to give you more problems. I don't think is helpful, because when you are preparing for the final, there is a lot of material to cover, and if I just keep adding more problems, that's not necessarily helpful. So I'm not going to add any more problems. And you have had a couple of midterms, so you have an idea of how these exams are. And between that and the homeworks, I think gives you a good idea where how this is going to be. So any other questions? So we have lost almost everybody in the class. There are only 6 people in the class now, right? So what is it? So why is it so difficult to show your face? Because it does help me, right? Because when I see a class of 25 people, I have a better idea of how a larger section of students is whether they are following or not. But if I see 5 people, the 5 people may understand, even if I don't say anything, they may understand the material. So it's really hard for me to have an idea of whether the class is following the material or not. Any other questions? Okay. So So your homework 6 is, set up. We can, start submitting it anytime. And I think it's due next Wednesday, I believe. But of course, you should, if you have time to get it done earlier, you should by all means do that, because obviously you don't want it to interfere with your finals. So when I say the deadline is next week, that's a deadline to give you flexibility, but don't get yourself into a difficult situation. So whatever date it says on the assignment is the, that is the final. So if I misspeak and tell you a different deadline from what it shows on Blackboard, of course, what you see on Blackboard is the right information. Okay. So so keep in mind that uh, you know right from the beginning of this semester, the policy is that you can form groups and you can work within groups, and that applies to all the standard ML programming components on your sixth assignment too, right? So you can work in a group, but of course you still have to submit programs individually, and you need to make sure that whatever you submit works without any problems, right? So we don't want to, debug your program, uh, and we won't debug your program, right? So it just has to work. Uh, if it partially works, then we may give you some credit. But if it just, you know, print some error messages and doesn't even start running, then you may not get any credit. Okay. And also keep in mind that, the ethics homework that you completed in the beginning of the semester, all of those uh, uh, you know ethical guidelines continue to apply, all the way, till you finish this course, and then of course for the rest of the courses that you take in the department, right? So especially for programming assignments, and even more so for short programming assignments like the one that you're being given in the sixth assignment, it is often easy to look up on the internet and find solutions, but that is against our policy, against the honor code, and of course if you are caught, then the penalties can be severe. But I don't think you need to worry about that in terms of the penalty, because I hope you have when you did the ethics assignment, you have learned the importance of learning the material as opposed to just uh, submitting the correct homework, right? And then after all, the homeworks don't count much at all, right? So they are less than a third of your grade, versus the exam grade is really what is going to uh, account for most of the final grade. So it is really not helpful to find uh, to short circuit the homework assignments, because in the end you obviously will suffer in the exam. Any other questions before we start on the course uh, review? Uh, One other thing that you should do is, we are uh, you I presume you saw my post about the weighted total for all the assignments and the exams you have had so far. So you should go check how you're doing in the course if you haven't done that already. You should also check whether all the assignments have been graded, whether there are any problems. You obviously should bring them up now rather than next week or week after that, right? So make sure that you just check everything, and everything is in order, and your weighted total is what you expect it to be, and whatnot, right? So if you have any questions, uh, post them on Piazza, uh, and or of course, you can ask your question here. Okay, so let's very quickly run through the topics that we have covered in the course. I'm, obviously I'm not going to go through, every concept in any level of detail, right? So this is more like, a list of topics than, any real discussion of any particular topics. So we started out discussing the first topic we covered is propositions, propositional formulas, uh, which consist of propositional variables and operators. And we just looked at these operators just now in ML. And we defined the notion of variables, and each variable in proposition can be either true Okay, so the variables can be true or false. And in order to evaluate a proposition, a propositional formula, somebody has to tell you, where for each variable, whether it is true or false. And then from that, you can go on and evaluate whether the whole formula is true or false. And based on that, we define the notions of validity, which means that the formula is true for all possible values of the variables in it, right? Satisfiable means there exists some values for these variables for which it is true, right? And then we have, equivalence of two formulas, which could be established in a number of ways. One of them is to use truth tables. And if you use truth tables, and for every possible assignment of values to the variables, if the two propositions, uh, are have the same value, right? So you have to try every possible assignment, every possible value for every variable. And if in every case the two propositions have the exact same value, then we say that the two propositions are equivalent, right? Uh, and um, So we studied this equivalence in more depth. We talked about how one logical operator such as and or implies can be expressed, right? So for the most common example is how do you take implication and express it in terms of and, are, and not, right? So that's one way to think about equivalence, where you take a single operator and say, how do you express if a proposition which has that operator using another proposition which does not have that operator, right? Uh, De Morgan's laws are another way of thinking about equivalence. It says, how to move uh, uh, negations inside, um, other operators, so that using De Morgan's laws, you can prove that certain propositions are equivalent. And then we looked at how some of these equivalence properties could be used to show that two different propositions are equivalent. And we had some problems on this in your exam and so on. Okay. And then we talked about normal forms, such as the disjunctive normal form, where you have all the disjunction operators at the outermost level, and then conjunctions, right? And then innermost level, there can be negation, right? So something like x1 and x2 are not x3 and x4, right? So that is in disjunctive normal form because the outermost, there is just one R. Next, inside, there is a conjunction, right? And then innermost is negation, right? So that's a disjunctive normal form. Similarly, we defined a conjunctive normal form where the roles of or and are interchanged, right? So in a conjunctive normal form, at the top level, you have all conjunctions, and at the second level, you have all disjunctions, and then at the third level, you can have negations, right? So negations are not should need not always be there, but if they are there, then they'll be at the third level. Okay, and then we talked about the satisfiability problem as one of the key problems in computer science, something that has formed the basis of a lot of theory on what problems can be efficiently solved and what cannot be efficiently solved, right? So there is the that's called the theory of NP completeness. It's not that I expect you to know what this is, but if you remember, great. Keep that in mind. If you don't remember, that's okay. Don't worry about it. Okay, so all you need to know, all I would like you to remember is that the satisfiability problem, which is this problem, right, is actually a very difficult problem in computer science, and there is no efficient algorithm to solve it. So one of the other things that we did throughout the course is, to study proofs. So how do we prove theorems, right? So how do we show that something is true? And the general approach for proving is we have some set of axioms, which you can think of as assumptions, which we believe to be true, right? So these are often uh, obvious to us, but we have no way of proving them from in any way. So then we just call them axioms, and then we also define inference rules, and from the inference rules and axioms, we come up with proofs. Uh, so we talked about I briefly talked about machine checkable proofs or formal proofs, but obviously that's not what we learned in this course. What we learned in this course are basically manual proof techniques, proofs that you can write by hand. We talked about how do you prove an implication. Well, if you want to prove an implication phi implies xi, then what you do is you start with the assumption that phi holds true, and then you want to show that assuming that this is true, that you can actually establish that psi is true, right? So assume that this is true, then if you can show that psi is also true, that means you have proved an implication. So what that means is that if you have a false hypothesis, so if this is just always false, then an implication is always going to hold, because if the hypothesis or antecedent, as it is called, if the antecedent is false, then the implication is always true. And this is called vacuous truth. Okay. So a second way of proving an implication is by taking the contrapositive, which means that the contrapositive of this is not psi implies not phi. Okay, so what that means is that you are basically negating both sides and then flipping the direction of the arrow, right? So whatever was on the right hand side now comes to the left, and whatever is on the left has gone to the right, and then we put a negation in front. So that is called a contrapositive. And one of the basic properties of propositions is that these two are equivalent, right? And because they are equivalent, you, instead of proving an implication directly, you can prove it's contrapositive. And sometimes it turns out to be easier to prove the contrapositive, right? And then if you want to show that two things are equivalent, so if you want to show that P is equivalent to Q, then you can do that by first showing P implies Q, and then independently you establish that Q implies P. Now you have proved P is equivalent to Q. Okay. So we talked about proof by cases where you say, okay, so when P is, again, you're trying to prove, something like P implies Q. And instead of assuming P is true, what you say is that whenever P is true, at least one of, you know, A, B, C, or D, depending upon how many ever number of cases, you're going to say that at least one of these is true, and then you show that if A is true, Q is true, B is true, then Q is true. And basically what you show is that in each case Q is true. And uh, since the only way P can be true is if by making one of these to be true, right? So that is a critical part of the proof. You need to have the cases completely cover P, which means that whenever P is true, at least one of these must be true, right? And once that holds, then you can chain the fact that you know A implies Q, B implies Q, C implies Q, and D implies Q, and P implies one of these, then you are able to go from P to one of these and then to Q, right? So that is the proof by cases. And then we have done many proofs by contradiction. And in the very end, we looked at proof by induction, right? So proof by induction and the well ordering principle have a little bit more of a clearer roadmap than some of the other proof techniques because, and that is only because uh, the induction proofs were applied in a context, in a particular context, whereas some of the other proofs we were, taking properties of various kinds from all over the place. So you may not have seen the structure in these proofs, but at least if you saw the structure in induction and well ordering principle, then and you learned how to prove using those two techniques, that is, then that's still a good result if you know how to prove those things. So we talked about predicates. The difference between predicates and propositions is that in the propositional formulas, all variables are either true or false. In the case of predicate formulas, the variables can take values from any set, right? So it can be from the variables can take integer values, real values, or values from any other set. That's the main difference between predicate and propositional case, which means that in the propositional case, everything is finite, right? Because the variables have only two possible values. But in the predicate case, the variables can take values from infinite sets, which means that it's evaluating formulas and checking whether a formula is true is no longer a straightforward task, right? So in the case of propositional formulas, it is a straightforward task. Sometimes it may take you a long time, but it is something that you can verify in a finite amount of time using something like a truth table. Whereas in the case of predicate formulas, you may or may not be able to prove the things that you want, right? So which is why we learn all these proof techniques, because often we want to prove things over infinite sets. And so we can't express them as propositions. We expect to express them as predicates and then use some of these techniques for proving them. Okay. But many of the concepts we developed in propositional formulas, such as variables, uh, giving values to these variables, and how you evaluate formulas, those are not particularly different, right? So they are basically the same. Again, the difference is that in the case of propositional formulas, the values are from the Boolean domain, so they are either true or false, whereas in the propositional case, the valuations are from arbitrary sets. So the concept of validity and satisfiability is again the same as the propositional case. We learned about quantifiers, and based on quantifiers, we could talk about free variables and bound variables. Bound variables are the variables that are quantified, right? Free variables are the ones that are not quantified. So when we talk about uh, variables uh, taking values, it is the free variables in a predicate formula that can take different values. The bound variables are, you don't have to uh, consider all possible values because the quantifiers will implicitly say how to, give them values. We talked about order of quantifiers, meaning how listing the quantifiers in different orders, changes the meaning of the formula, right? So if you have a there exists and for all, if you change their order, then the meaning of the formula is quite different. Obviously, if you there is no such thing as changing the order of two for all quantifiers because you know they are both the same already, right? So, and we also talked about negating quantifiers, in particular, how for all is essentially the same as, not of there exists not, and the same way, right? And one of the things exercises we went through is to start with a statement in English and converting that into a logical formula as a way for us to uh, express in a precise way what we want to express, right? So when we write it in English, most of the time some ambiguity creeps in because English is not a it's meant for humans to communicate, and it's not designed for precision. And whereas logical formulas are designed for automated reasoning procedures and computers, and as such they have a precise meaning. So if you write it down, there are no two ways of interpreting what's written down. So the next topic we looked at is sets. So what is a set? We learned the set builder notation, something like, uh, you know, right? So that's a set builder way to define the set of odd natural numbers, right? So, and then we went through the concepts of membership, subset, union, intersection, and difference. Uh, and we looked at properties of these operators, such as commutativity, which means that, A op B equals B op A. That is commutative, which basically says that the order of the operands can be switched. Associativity says that, A op B op C can be parenthesized in two different ways, and both ways of parenthesizing are equivalent. That is called associativity. Distributivity involves two operators, and one of the examples that we considered is A union B intersection D equals A union B intersection A union D, right? So this is, you are distributing the union over intersection, which basically means that you are, uh, you know, basically moving the union inside the intersection, right? So that is called distributing. And if doing this distribution preserves equality, then you say that that particular property, the distributivity property holds, right? So we talked about how to prove equality of sets, which basically means that you show that A is a subset of B and B is a subset of A, means A equal to B, right? So this is how you prove equality, right? Or another way to do this is to say that every element of A is also an element of B, and every element of B is also an element of A. Then once again, you're able to prove that two sets A and B are equivalent. We talked about universal sets. How do you do complement of sets, and De Morgan's laws as it applies to sets, as opposed to De Morgan's laws as they apply to Boolean algebra, right? So that's what we did before, but now here we are doing De Morgan's law on sets. We talked about power sets and Cartesian product on sets and how that relates to tuples. So then the next topic we discussed is functions and relations. Functions are a special case of relations. So mostly we looked at relations first. So we define codomain, right? So we often define a relation as something. A binary relation involves two sets A and B. We often write, draw a circle A, draw a circle B, and then whenever there is a relationship between two elements, one in A and one in B, we represent them by drawing arrows. So let's say this might be A, B, C, and D, right? So this is how we often refer to or represent or pictorially represent relations. And the domain is the set A, right? So this is called the domain. This is called the codomain. And support is the set of all points here that have an outgoing arrow. The range is the set of all points in B that have an incoming arrow, and so on. And a couple of lectures ago, last Thursday, we went through an example involving, not last Thursday, but yeah, the week before. So we went through an example of how to represent relations in standard ML, and in that we explicitly computed these, support and range and so on. Okay, so so whatever I'm defining now is we also went through the effort of precisely capturing them in using standard ML. We can also represent relations over multiple sets. And the way we do that is by thinking about Cartesian products. So for instance, we could have a ternary relation S, which may involve three sets, which we could represent in this way, right? So A cross B to C, right? But then A cross B is simply another set, right? So this is why we don't specifically, think about ternary relations or quaternary relation or relations with, many over many sets, because we ultimately will, can think of them as binary relations on, Cartesian products of other sets. So as a result, we always, focus on binary relations. We talked about properties of binary relations. What does it mean for a relation to be a function? What does it mean for it to be a total function? What does it mean for one-to-one, or injective is the other term that we used, or onto, which is also called surjective, and bijection, which means that it is satisfies both one-to-one and onto properties. So we talked about uh, function composition, right? So the composition of two relations, function composition is just a special, again, function being a special case of relations, function composition is no different from relational composition. And relational composition, what we do is that we have one relation from, let's say, A to B, let's call this R, and another relation from B to C, let's call this S. Then the composition is, right? The composition is simply going to connect this element to that element, right? So essentially what it says is that if you can go from A to C by going through some point in B, then you can connect A and C here directly, right? So that is called the relation R composed with S, okay? So, and if you happen to have a relation that goes from A to A, then you can apply this composition again and again because, you know, because when you compose R with R, right, that is still a relation that goes from A to A. And when you compose R with itself n times, then that is what we call as R to the power n, right? So, and finally, we talked about inverse of relationships, right? So, so that's roughly the set of topics we went through on relations. Then we said that relations can be represented as graphs, right? Especially, so in particular relations on a single set, right? So a relation that goes from a set to itself is of particular interest. And these relationships can be expressed using a graph, right? And the main point is that see how we are drawing two circles here because we have two sets, A and B, right? So if there are no two sets, if it's exactly just one set, then we don't need these two circles and we don't need any circles at all because you know, everything is one set. And but we still continue to draw arrows in this manner, and you know, what we end up in that case is a directed graph, okay? And now this directed graph has more interesting properties than what we see here because here the arrows all start on the left side and all end on the right hand side. So there is no such thing as, you know, following the arrow and then from there going somewhere, right? So there is no next step for you to go in this graph. But if there is just one set, then, you know, you have you are able to go from, you know, A to B, and then you may be able to go from B to you know, D, and B to maybe E, and so on, right? So, and that's what we call as a directed graph. And then we can talk about interesting properties of these graphs, such as how the degrees, if you sum up the, you know, in degree, which is the number of arrows coming into a node, right? And out degree, which is the number of arrows going out of a node. And you sum up these in degrees and out degrees over the entire graph, then they will add up to be equal, right? So there are some interesting properties of graphs that we looked at. We looked at what is a walk in the graph, what is a path in the graph, and how walks relate to relational composition, right? So if you have a walk of length 2, then that is related to you know, R square. So if you have a walk of length n, then that is related to you know, R to the power n, right? So if you can go from A to, so what you can say is that so if there is a walk of length n from A to F, then we can say that A is related to F by r to the power n, right? So that's the relationship between walks and relational composition. So there is this nice geometric or pictorial interpretation of all of the things, all of the concepts that we have looked at here in the case of, relations on a single set, because we can write this down as a graph, and then there is a graphs are quite intuitive. Things like walks, paths, and so on are very intuitive for us, and therefore it gives us a more intuitive way to understand things like composition of relations. We talked about shortest paths, and the shortest path between two nodes is called a distance, right? We talked about a special type of graphs that contain no cycles, right? And if they don't contain no cycles, then we can use what is called topological sorting on them. And that gives us, and then we used an example of, course prerequisites as to illustrate this, the concept of DAGs. So we looked at Euler's and Hamiltonian circuits, how Euler's circuits are very easy to compute, and how Hamiltonian tools are, very difficult to compute. Okay. Then we looked at types of relations. What is a reflexive relation? What is a symmetric relation? What is a transitive relation? And then, antisymmetry and irreflexive. And then we talked about how partial order is something that a partial order is antisymmetric and transitive. So combinations of these relation types, we give them new names such as partial order, equivalence, and so on. And then we talked about closures, taking a relation and forcing the relation to be reflexive or symmetric or transitive, right? So that's something that we call as closure. And how to compute these closures is something that we discussed. Then we spent quite some time on cardinality of sets, right? In particular, cardinality of infinite sets. And we talked about how to count the number of elements in an infinite set, right? And we said that we could use the concept of surjection, injection, and bijection to reason about the number of elements in infinite sets. Okay. And then we defined countable sets, which is sort of the smallest infinite set that's possible. And then uncountable sets, which are larger sets, right? And we showed that if you take any set S and you take the power set of S, we showed that the power set of S always has more elements than S. And that gives us a way to construct larger and larger and larger sets. And the way we prove that a power set is strictly larger than a set is using an argument, using a style of argument called diagonalization. And in particular, we learned how Cantor's diagonalization proof works to show that S and P of S have different sizes no matter how large S is, right? We also studied, uh, you know, one or two other examples of diagonalization that aren't Cantor's proof, but we for instance proved that there is no way to enumerate all real numbers, right? So we have a simpler diagonalization proof, whereas the Cantor's proof is a little bit more involved. So when we want to prove countability, there are a couple of options. One is that you specify an enumeration order, and the important point is that it's not enough to just say there is an enumeration order. You need to make sure that every element will eventually appear in this enumeration, right? So if you can't guarantee that, then you haven't proven that it is countable, right? So you do have to, this is a very key requirement, right? And the second way to prove is using these mappings, right? So here is a definition of when two sets have the same number of elements, or one set has more elements than the other, and so on. So you can use that definition to prove the cardinality, or you can rely on closure under a union, product, and various other set operators, right? So when you have a question in the exam, I will specify which technique you can use, or I might say you can use any technique that you can think of. So so that's all the material, I guess, that we covered before the first midterm. And after that, we looked at summation techniques. I'm not going to, so the material after the first midterm is a little bit more recent. So I'm going to summarize the material more quickly. So we looked at three main techniques for summation. One is called perturbation method, which basically involves rearranging the terms in such a way that somehow we can get a closed form solution. So this is not a precisely defined technique, right? So that's why we just give you a few examples, and the examples sort of give you a general idea, but they also tell you that this is not a uh, completely specified, fully specified method. It's more of a uh, strategy to search for how to how you could compute a sum rather than an exact method. But using that method, we proved how do you do geometric progression, arithmetic progression, sum of I to the power k, and so on. And all of that is something that you can keep in mind. So then we showed that you can use calculus, and in particular differentiation and integration, to add up um, sequences. So using differentiation, we looked at what is called arithmetic or geometric progression, where you have both an arithmetic component, which increases linearly with from one term to another, and a geometric component where there is an exponent that changes from one component to one term to the next. But the more powerful technique is the integration technique, which does not give you an exact answer, but it gives you a bound. So it gives you a lower bound and upper bound. And so in computer science, most of the time, uh, we want to have an estimate, and if the estimate is close enough, that's all we care, right? And there are times when we are happy with an estimate which is within a factor of 2. Sometimes we may not even, we may even be okay with a factor of 10. And there are other times when we want the number to be within a few percentage. And again, uh, these bounds tell you, what is the how much error could be there, and based on that, you can work with an approximate sum rather than an exact sum. So the next unit was counting, right? So we spent several lectures on counting. And the basic way we count is using bijections. Um, we were not very explicit about specifying the bijection, but that's always, what is in the background. So what we are trying to do is we are trying to say the number of ways of doing one thing can be counted by is the same as the number of ways of doing some other task. And essentially that's where the bijection comes in, right? So instead of studying the original problem, we study a different problem. And uh, the best examples of this, came through uh, counting binary sequences, right? The sequences of zeros and ones. And uh, in particular, we showed how you can take a sequence of zeros and ones and we can interpret them as a procedure for picking a unique element. So for instance, if you have number of subsets, it can be mapped to a sequence of zeros and ones by essentially saying, so this says pick the second element of the set, the fourth element of the set, fifth element of the set, and seventh element of the set, right? So that's what I mean by interpreting the sequence as a procedure for picking, right? So the sequence tells me pick the second element, fourth element, fifth element, and seventh element, right? So if we have a way of representing each unique way to uh, pick an element as a binary string, and if we can show that every binary string corresponds to one way of uh, picking a unique element, then we can simply count the number of possible binary strings as the count, right? And we use that to count the number of subsets, the number of subset sequences, the ways an integer can be partitioned, the way you can have an increasing sequence of integers. There is a balls and bins problem, which basically says that you have m balls and n bins, right? So we looked at a problem like this in your second midterm. I think maybe it was called pegs and something else, but it doesn't matter, right? So there are balls and bins, and if you toss m balls into n bins, and any ball can go into any bin without any restriction, then again that problem can also be modeled in terms of these binary sequences. So if there is one thing that new that you should have learned from this course, that is this way of doing the counting, right? So the rest of what we did about counting using union and disjoint sum, Cartesian products and inclusion and exclusion and division rules and so on. Some of you may have seen this in come across these rules in other courses that you might have taken somewhere else. But this is something that is a really neat way of looking at counting problems. So the very last thing that we looked at in counting is the pigeonhole principle, right? So that's and counting is closely related to probability. The particular type of probability that we looked at is called discrete probability, because we are working with discrete sets as opposed to continuous sets like real numbers or rational numbers, right? So probability is so we call this discrete probabilities. We defined terms such as variables, outcomes, sample space. What is an event? Event is nothing but a set of outcomes, right? And then we talked about uniform probability spaces, right? And in uniform, when the probability space is uniform, which basically means that every outcome is equally possible, then the probability ends up amounts to basically a counting problem, right? So basically we want to, because if every outcome is equally probable, then the probability of an event, right, which is a set of outcomes, simply becomes the size of the set, right? So therefore, probability problem just reduces to a counting problem. Okay. So we showed how many things that we learned in set theory can be very directly applied to probability, and can be used to compute the probability when you if you have a probability of A and probability of B, right? A and B are events, which again are sets. Then you're asked what is the probability of A union B. Then this is a counting problem. If A and B are disjoint, then we can simply add the sizes of A and B. If A and B are not disjoint, then we end up applying something like inclusion exclusion principle to find the size of A union B, right? Then we looked at conditional probabilities and the tree diagrams for analyzing problems involving conditional probability. We also looked at medical testing, and we saw some unintuitive results where what seems on paper to be a very accurate test can end up generating a very large number of false positives. So that's something that we need to be careful about when we use conditional probabilities. So the last few topics that we looked at are recurrences and recursion. We talked about how do you compute using recursive functions. So this is our transition to thinking about programming. So you want to compute something. If you can define it as a function, then we can use whatever we know about functions to do the computation, right? And very often we end up with recursive functions. For anything non-trivial, we end up with recursive functions. And one of the things that we try to get you comfortable with is in thinking recursively, right? And it's something that you are going to get better throughout your the next few years, right? Because the recursion is the essence of programming, right? And so you will, if you haven't, if you don't feel comfortable yet, you will feel comfortable. That'll come gradually as you do more and more programming. So we talked about asymptotic complexity and the O notation, and we talked about how to solve recurrences using three techniques, right? So since we covered this material so recently, there is no reason to go through that in very much detail. And then the last several lectures, we were really focused on recursive functions, recursive data types, and programming using standard ML, right? And right in here, we talked about induction, and very briefly, I introduced the concept of proving the correctness of recursive definitions, right? So most of our programs are, can be thought of from a mathematical perspective. Most of our programs are nothing but recursive definitions. And if we want to be sure that they are correct and they do what we want them to do, then we need to prove them to be correct. And that's where induction comes in handy. And the main reason why induction is proof using induction is emphasized in computer science is because induction proofs come very naturally for recursive definitions, right? So anytime you have a recursive function, then the proof is going to be based on induction. So if you understand induction, then you have some chance of proving your program correct, okay? And then we spent a fair bit of time doing standard ML. And one of the things that I wanted to capture in using standard ML is to take many of the concepts that we have covered in the course, such as propositions, predicates, sets, and operations on sets, right? So we wanted to show how all of them can be expressed in the language of ML, right? So we can express mathematical definitions as programs in standard ML, and then we can have these programs execute so that what we have is a executable definition, which gives us another way to check whether our definition is correct or incorrect, right? So we also looked at relations. How can you express relations as data types in standard ML? How can you look at graphs? Uh, um, how can you do counting problems? How can you write a program to do counting? Um, and probability can also be dealt with using programs in standard ML, but I didn't really introduce that because um, the way you think about probability is in conjunction with random number generators, right? So what you do is that instead of calculating probability the way we have done in the course, programmatically, what you would do is you would generate random numbers to, essentially create scenarios and think about outcomes. You would use random number generators, and these are somewhat painful to express in standard ML, so I decided not to show it. But the point is that very often in computer science, one of the things that you do is that counting is good, uh, you know, analytically calculating probability is good, but sometimes you're not sure whether you got it right, right? So in a course, you you have an exam, your instructor is there to check whether your calculation is correct. But in real world, right, so there's nobody to check your work. And so by so one way you sometimes are able to check is by writing a program, right? So you have a probability calculation that you want to do. You calculate with pen and paper. You are not 100% sure, then you can also write a program and see whether your program generates the same answer. Well, then you can be sure that then you can be more confident that you are right, right? So the technique doesn't always work because, well, sometimes the number of possibilities are, far too large for your computer to, crunch through. But many times the it is not that large, and then we can in fact do it programmatically. So let me just end with just this one last slide that kind of gives you an idea of where all of what you learned, where does it take you, right? So so propositions and predicate logic are going to feed into many courses, and I'll just mention some of them here. Computer organization, which is actually called Systems 1 or something like that. Okay, so it's a course that you're probably going to take in the spring of next year, right? So it's about how hardware works, and hardware works using Boolean formulas, right? So that's why propositional logic is central to computer organization, right? And logic is also plays an important role in databases, and a lot of what we learn will be very useful in two courses that will appear again and again. One of them is theory of computation, which most of you will take in exactly in the next fall, and algorithms, which most of you will take in the next spring, I think. So, so the material that we cover is most relevant for these two courses, right? So because without the material, you will not be able to start any of these, either of these courses. But in addition, it also feeds into some courses like 220. Proofs are things that we have in most CS courses. Once again, you will see more of these proofs in theory of computation and algorithms. Relations are very important in databases because very often we work with relational databases. So if you, that's how relations come into picture. Graphs. So a lot of things that we learn in algorithms is based on graphs. A lot of things we do in computer networks is based on graphs. And in addition, there are some applied math courses that are required in your computer science. One of them is 301. AMS 301 has a some amount of overlap and a good deal of complement with the 150 course that we went through, right? So 301 covers graphs, it covers counting, and depending upon who teaches it, you may have some summation and some recurrences and so on. So hopefully that'll help you, not forget some of the material that you learned in this course. So probability and counting are also very important concepts in artificial intelligence and machine learning, right? So a lot of machine learning is based on, probability and statistics. We didn't do statistics here, but at least the probability part is going to be useful there. And finally, recursion is really, everything in programming. So you are going to, pretty much every course you will learn, more recursion. And okay, so that's all I have for today. And I will, as I said, I can have some review session next week. I will post a poll on Piazza, and if there is sufficient interest, then we'll have some review sessions. And if there are review sessions, the important point is for you to come to the review session with, specific problems or topics that you want me to cover, right? And you can tell me in advance if you have them, if you know them in advance. Otherwise, you can come to the class and we can take it from there, right? And obviously, all these review sessions are optional. If you think you're already doing well and you don't need any more help, good for you, right? So don't worry about it. You don't have to show up. I only for people who need help, I'm available to help. Otherwise, it's been great teaching this course. Hope your final goes well, and hope I'll see you again in some other course during the next 4 years. So if there are any questions, I'll take them. Otherwise, feel free to hang up and enjoy the rest of the semester.